As I said, if at least one C prime ij is positive, then the solution is not optimal. In order to find the optimal solution, we need to perform iterations. I will select the largest C prime ij if there's more than one positive C prime ij. Then this will be the entering variable. The leaving variable, however, is determined using the stepping stone method, which is basically a way to determine the chain reaction that would result from increasing the value of the entering variable from 0. Here we have the same transportation table. However, the initial solution is obtained using the northwest corner rule. And we have calculated the UIs and the VJs, and also the C prime IJs for all the non-basic cells. As you see here, the largest positive C prime IJ is in this cell. There are other positive C prime IJs like here, but the largest one is the 4. So this becomes the entering variable. Once I determine the entering variable, I want to figure out what is the leaving variable. In this case, this is the entering variable, as we said, the largest positive C prime ij. I can find the leaving variable using the stepping stone method. And that stepping stone method says, starting from the entering variable, you can go left, right, up, or down, stepping only on basic variables, and thus the name stepping stone, meaning that those basic variables become like stones, you can step on them. So starting in this cell now, I cannot go left because there are no basic variables. I cannot go down because there are no cells at all. I can go either right to this basic cell, or I can go up to this basic cell. So either way is fine. I'm gonna go right to this basic cell, and once I'm here, I can go either to this basic cell or to that basic cell. But if I go this second basic cell here, I cannot go left because there are no basic cells to the left of it. There are no cells at all to the right of it. I cannot go back, obviously, but I can continue only. So that means as if I just jumped from this basic cell to that basic cell directly. So, and once I'm at this cell, I have to go, I cannot go up, I have to go left either to this cell or all the way to this cell. But if I go all the way to this cell, then the next step, the only option I have is going up here and then left here, and then once I'm here, I'm stuck. I cannot do anything. I cannot go down because there are no basic cells. I cannot go left. There are no more cells. I cannot go up. Which means to begin with, I went too far. I can now go back to where I was right here instead, and then I will go down from this point here, and thus I will end where I started. So the whole idea is to start and end at this entering variable. Now I still did not determine what is the leaving variable, and I do that once I have established this cycle or chain reaction. I will put pluses and minuses. I will put pluses and minuses. As you see here, there's a plus on the starting with a plus on the for the entering variable, and then a minus here, and then a plus here, and then a minus here, only at the corners of this cycle. So that means I have to add some amount to the cell such that I will not make any of those cells negative. So I look at the most negative cell, so the minus 90 here and the minus 300 here. The smallest negative is actually the minus 90. The smallest negative in absolute sense, obviously. So 90 is the smallest number, the one that has this negative to it. So I'll go with 90. So that means 90 I will have to add 90 here, subtract 90 from here, add 90 from here, and subtract 90 from here. Okay. The new allocation becomes the one we just added a 90 here, and then we subtracted a 90 from here, and then added a 90 to this one and subtracted 90 from this one, and thus this is a new allocation for the transportation problem, a new solution. Now the question is this optimal or not? To figure that out, I have to repeat the calculations for all the UIs and the VJs, those multipliers, and then also recalculate the C prime IJs for all the non-basic variables, and then figure out if there's any more positive C prime IJs left, then the problem is not optimal. If all the C prime IJs are negative, then the problem becomes optimal. So let's recalculate those multipliers. The new UIs and VJs are found here, similar to what we said before, starting with u1 equal to 0. I will find all the other ui's and vj's by going to all the basic cells. For every basic cells, ui plus vj equals cij. For example, u1 0 plus something is 16. This something must be 16. So u1 plus v1, so 0 plus v1 equal to 16, v1 must be 16, and so on. 0 plus something equals 13, this something must be 13, and that's how I found v2. So 0 plus v2 equal 13, this something must be, or this v2 must be 13, and so on. Once I have this 13, I can find u2 by saying that v2 plus u2, v2 13 plus u2 equals to this 13. That means u2 is 0, and so on. So this will allow me to find all the other ui's and vj's by applying this formula ui plus vj equals cij only for basic cells. Once I'm done with those ui and vj's, I will calculate the c prime ij's for all non-basic cells. And for example, this c prime ij here will be, I'll say ui 0 plus vj 19 minus cij 22 equal minus 3. And similarly, this minus 2 is from 0 plus 15 minus 17 is minus 2. So I apply that for all these non-basic variables to get all the c prime ij's. Once I have all these c prime ij's, I will check if there's any positive c prime ij's, and I do have a bunch of them, like here and here. So that means the problem is not optimal. So I will select the most positive, and in this case there are two positive numbers, both are 2, so I will break ties arbitrarily. Let's say that this, I'm going to select this one as the entering variable instead of that one, even though they're both 2. Oh, I actually have selected this one as the entering variable, not that one. Sorry, but since this one is selected, I can go right or up. Both are fine. So if I go right, if I go all the way right up to here, then there's nothing I can do. I can go here, then I can't go anywhere else, or I can go here, then down, then nowhere else. So I know I'm mistaken. All of these are not correct. So I go all the way back to here, and then I will go up, and then I go left, and I can go down. I close the loop. And by the way, these stepping stone cycles are unique. That means there's only one of them, so there's not multiple ones for the same problem, and you have to be careful how to find them. But anyway, now we have plus here, minus here, plus here, minus here, and the one I look at only the ones that have minuses. That I look at the cells that have minuses only, and I find this is the 40 and this is the 100. The minimum is 40, so that means I will add 40 to this new basic cell. So becomes 40, this becomes 0, and this becomes 140 if I add to it the 40, and this becomes 60. So the new solution is here. And this new solution, it could be optimal or not, and I will have to repeat by recalculating the UIs and the VJs to find whether, and the C prime IJs to find whether this is optimal or not. So go here and then we find out that these are the new set of UIs, new set of VJs, and the C prime IJs for all the non-basic cells. We have -1, we have 0, we have -2, we have 0, we have -14, -9, -4, -8, and -5, which means there are no positive C prime IJs, which means that the problem is optimal. For the zeros, for now, just ignore them. It's a special case actually, which means there are alternative optimal solutions if there's a C prime IJ of 0. But for now, let's just treat it as there are no positive C prime IJs, which means the problem is optimal. I'll talk about the special cases in the next few slides actually. Okay, so this is optimal, and the solution is Z equal 10,330, and we figured that out obviously from multiplying this 60 by the 16 plus 140 by the 13, and there's not a location here, and the 40 by the 14, and 210 by the 19, and so on. Only for the basic variables you end up with this cost function or this Z function, and this is the optimal solution, basically showing only the connections between the sources and the destinations for the allocated routes. Here is the Excel solution for the transportation problem, and you could use the Jensen solver or the Jensen add-in to solve this transportation problem. I recommend that you at least try one problem using Excel, one transportation problem using Excel to practice. The assignment problem is a special case of the transportation problem, where in the assignment problem we have n sources and n destinations, and I have to map the sources to the destinations as if the capacity of the sources is 1 and the requirement or the demand on the destinations is also 1, and then you have to kind of match 1-to-1 or ship 1 unit from a supply of capacity 1 unit to a destination of demand of 1 unit. Thus, it's very similar to the transportation problem, except, as I said, we have an equal number of supplies and demands. So, and each task or each supply must be matched with a destination. It is similar to assigning you have n jobs to be matched or mapped to n people, and there's a mapping cost associated with this assignment. That means if you assign person 1 to job 1, there's a cost C11, and if you assign job 1 to person 2, there's a cost C12, and so on. And I'm trying to find the optimal, which is the minimum cost assignment for all the jobs. As I said, the assignment problem is a special case of the transportation problem. However, it has the same number of sources and destinations, and all the supplies and demands are 1, the capacities and the demand. Here's an example: 4 ships to transport 4 loads from a single port to 4 separate ports. That means ship 1 and 2, 3, 4, and port 1, 2, 3, 4. All are the ships. Here are the ports. And then if you use ship 1 to transport this load to port 1, then the cost is 5. and so on. This is called a assignment cost table. Here's the network representation of the same problem. You can see here that there are 4 nodes for each of the sources, and there are 4 nodes, exactly same number for the destinations, and I'm mapping. If you map source 1 to destination 1, the cost is 5 units of cost, whatever that is, and so on. The rest of the costs are read that way. The decision variable in this problem, this linear programming problem, are binary. That means xij is a decision variable where it's 1 if ship I is assigned to port j and 0 otherwise. So they are binary decision variables. The LP is easily formulated as double summation of Cij times Xij, and I want to minimize this quantity, which is the assignment cost. There are, similar to the transportation problem, there are 2 types of constraints, the supply constraint and the demand constraint, and remember that both have a value of 1 on the supply capacity and the demand requirements. And obviously there are the non-negativity constraint. So that means here for the supply, that means you cannot assign more than 1 person to the same job, and then this means that a person cannot be assigned to multiple jobs. And there are those 2 n constraints, n plus n constraints for this problem. Again, this problem is a linear program, and I can solve it using the simplex method or using the transportation algorithm. However, it's also a special case of the special case, since we said that the transportation algorithm is a special case of the simplex method, and now we have the assignment problem is a special case of the transportation algorithm, which is even a simpler way of finding an optimal solution, which we will see in the next few slides. However, this is saying that since the assignment problem is a special case of the transportation problem, then the solution must be equal an integer, and that's the modularity property that we've seen in the previous slides. So that means no assignments such like these will happen. Fractions assignment will not happen. You will only have integer solutions, which what we want here actually, without having to guarantee this through the formulation of the linear program, that we will get an integer solution for this problem guaranteed without having to do an extra effort in the formulation. That means we just do not have to worry about putting in the mathematical formulation that this problem has only a binary solution or an integer solution. Also, if you want to prohibit a certain assignment, you can use m as a very large number. That means person 1 can be assigned to job, let's say 7. So C17 will be equal to m, which means it is a very large number. So it will prohibit the assignment of such thing to happen. Here's an example. Assign students to mentors. You have 3 students and 3 mentors, and they need to be mapped to each other. And obviously the supplies are 1 and the demands are 1, so this is in a transportation table format in a way. So how to solve this assignment problem? As I said earlier, this is a linear program, so you could actually use the simplex method, but also this is a transportation, a special case of transportation problem, so you could also use the transportation simplex approach. However, because if it is a special case, that means it has even a simpler approach to get an optimal solution. This is called the Hungarian method. So we will use the Hungarian method to find the optimal solution for the assignment problem. The Hungarian method is as follows: subtract row minimums from each element in the row. So you build the assignment table, and then in that table subtract row minimums from each element in the row, and then subtract column minimums from each element in the column, cover all the zeros with as few lines as possible. That means, will you be able to cover all the zeros inside the table with the minimum number of uh, hidden columns and rows? We'll see in the next slide how we do that. If the number of lines used to cover the zeros equals to n, then the optimal solution have been reached, and you just have to determine it and find it by allocating those mappings in the zeros locations where you see a zero inside the table. Otherwise, the minimum cost is not found yet. That means if the number of lines is not equal to n, and then what you need to do, subtract, find the minimum cost that is not covered by the lines, subtract this minimum cost from all the uncovered elements, add it to the intersection of two lines, and then repeat by covering all the zeros again. Okay, once you have the number of rows and columns that cover all the zeros equal to n, then you're ready to find the optimal solution. So how do you locate the optimal solution? It says make the assignment one at a time, the mapping one at a time in positions that have zero elements. So you only allocate where there are zeros inside the matrix. Begin with rows or columns that have only one zero. So try to locate a row or a column that have only one zero in it. So actually a row and a column that have one zero in it. If you can find that out, then make the allocation there and then cross out the row and column involved. Once you do that, move on to the rows and columns that are not yet crossed out. Try to find out a new location where there's only one zero in the row and column, and then assign it, make the mapping in that cell. Continue until every row and cell has exactly one assignment in it. So it's kind of like iterative, and you have to look for it yourself. So let's do this example that we showed earlier. We have three students, Harry, Draco, and Goyle, and three mentors, Snape, McG, and Lupin. We need to map them to each other. As the algorithm says, find the row minimum. So the row minimum here is 2. Here's the row minimum. 2, you subtract 2 from every element in the row, and then the row minimum here is 1, and then you subtract 1 from every element in the row here, and the row minimum here is 2, you subtract it from every element in this row. Thus the result is 301. By subtracting 2 from 5, this is 3, 2 from 2, this is 0, and 2 from 3, this is 1. And then subtracting 1 from each element in the second row gives us 0, 3, and 4. And subtracting 2 from each element in the third row gives us 0, 2, 2. Now we determine the minimum in each column now, and the minimum is 0 in the first column, the minimum is 0 in the second column, and the minimum is 1 in the third column. We subtract 0 from the first column, 0 from the second column, and 1 from the third column, and the result would be 300 is unchanged because the minimum was 0 in the first column, and the same thing for the second column, it's unchanged because the minimum was 0. However, in the third column, the minimum was 1, and the result would be 0, 3, 1, which is subtracting 1 from each one of these elements. So now the algorithm says try to cover all the zeros using the minimum number of rows and columns. For example, if I cover all the zeros here, I can cover those zeros, and then these zeros and those zeros. So I'm using here 3 columns, but this is not the minimum number. It says try to use the minimum number. So the minimum number actually is found by covering the zeros this way, and then using a row to cover the zeros that way. So 2 is the minimum number of rows and columns used to cover all the zeros. Thus, this number 2 is not equal to n, the original number of students or mentors. and that means we cannot find the optimal solution right away. So the algorithm continues to say, in this case, find the minimum uncovered cost, which in this case it's 1. So subtract this from all other uncovered elements. So from 3 minus 1 is 2, 3 minus 1 is 2, and 2 minus 1 is 1, and obviously 1 minus 1 is 0, and add it to the intersection of the covered elements, which is only one intersection here. So the 3 plus 1 becomes 4. Thus, we have this new matrix. Now, it says try to cover all the zeros using the minimum number of rows and columns. In this case, I'll try to use this 1, 2, and I still have to use a third, either a row like this to cover all the zeros, or a column like this to cover all the zeros. In either ways, sorry, maybe not this column, maybe another row, a row like this to cover these zeros. This 0, yes. Whatever you do, or maybe this column, yeah, cover this 0. So either ways, whatever you do, you will need at least 3 of these lines to cover all the numbers, which means now the minimum number of rows and columns used to cover all the zeros equal to n, and thus, which is 3, and thus look for the optimal solution under the zeros. And as the algorithm says, try to map here, look at a row and column that has only one zero. For example, this zero, well, there are another zero here in this row. There is okay, there is another. If you take this one, there is another zero in this column, and this one same thing. So you cannot actually do the assignment with try locating a zero that which is the only zero in its row and column. However, so you can now allocate Harry to make G, and thus you remove this row and column, and then if you allocate a Draco to Snape, that means we using this zero, that means we remove this row and column, then we end up only automatically by allocating a Goyle to Lupin. It may not work out directly the first time right away. You may have to do a few iterations before you figure out the final optimal solution.